Hello, everybody. After Gabor's presentation, I will now present you from the work he has developed over the last 15 years on formic acid, how we bring this into a product and how it is integrated into a more broad view of energy storage and how we want to push this furthermore. So, quickly, formic acid. Why are we interested in formic acid? Because it's easy to transport and store hydrogen, and ideally for fuel cells application. Why? Because it's a liquid at ambient condition, and we have it's easy to handle, quite high density of hydrogen, because it's let's say equivalent to the 700 bars hydrogen storage, and almost 1 kilowatt of electrical energy stored into 1 liter of formic acid. And we have a low-cost reforming process at low temperature, so below between 50 and 100 degrees. So how do we use that? So we set up a project to demonstrate this part, the energy release part, how to produce electricity and heat from the formic acid with the use of the fuel cell. So based on the catalyst development made by Gabor Lorenzi, we called it the HyForm reformer to convert the formic acid into a gas mixture of hydrogen and CO2. And we use this hydrogen into a fuel cell to produce electricity, to make it rather simple. The first application and demonstration we've made here is stationary power generation, so with the objective to improve the hydrogen storage for fuel cells application like off-grid or backup units with a liquid fuel and not a gaseous fuel, and compete with methanol, for example, which is used in some case already as hydrogen carrier. So the project objective was to integrate the reformer, so this formic acid reformer, into and combine it with a fuel cell, PEM fuel cell in this case. So just a simple sketch to explain you how it works. So from the liquid formic acid, we have a reformer where we convert this liquid formic acid into a gaseous mixture of CO2 and hydrogen, and we need a little bit of heat that is recovered from the post-combustor. Then we have the fuel cell, which converts most of the hydrogen into electricity and heat, or into water producing electricity and heat, and the remaining part of hydrogen is used to heat up, or maintain the heat up the reformer. So this is the basic principle of the system. Now, how we made it has look like an integrated unit. So we took a commercial unit to demonstrate that the technology is, I would say, compatible with existing units. We took a 5 kilowatt system, but let's say that we had to downgrade to 1 kilowatt for economic reasons. The cost of systems is still quite high for fuel cells. But let's say that we developed the control and safety and the hardware, the software, design a specific reformer in order to fit with the the power demand, the gas flows, and the recuperation of the post-combustion heat with a specific catalytic post-combustion. In order to replace the standard natural gas reformer that is in place in the standard system. Then we had to build, assemble all together, and finally test with some, I would say, with some cycles to fine-tune the systems, how to control fuel cell and the reformer at the same time, to combine, to have a good integration and produce electrical power. So the team was composed of the EPFL group of Catalysis for Energy and Environment, GRT group, thanks to the financing support of the Swiss Federal Office for Energy, and in-house engineering for the fuel cell part. The project was started in 2015, was system design and procurement. In 2016, manufacturing and delivery of the fuel cell and components, individual component testing, and 2017, so last year, assembly of the reformer and test of the reformer and the full test campaign. Just to make it short, what is the main project results? So we integrate in this machine on the right-hand side the fuel cell and the reformer. So this machine is liquid fueled with pure formic acid. And we had continuous and stable hydrogen production and continuous and stable electrical production, thermally self-sustaining. So the reformer used the heat of the fuel cell and the post-combustion. And we obtained 40 to 45% stack efficiency over a range of power from 400 to 950, so almost 1 kilowatt. No degradation observed during the operation. So just two curves to illustrate that this is kind of IV curve with the power and efficiency over some formic acid consumption. And here, just to illustrate the efficiency we obtained at different power, depending on the different, I would say, operating conditions and power, but rather stable power and efficiency over a wide range. Okay, so now which market do we target with such kind of application? So as I mentioned, off-grid backup power generation unit, because it's easy to fuel and refill because we have a liquid fuel. We made this demonstration with a PEM fuel cell, but solid oxide fuel cells are also fully capable of using this mixture of hydrogen and CO2. Quickly on the advantage that we can show a low temperature reforming between 40 and 90, 100 degree. We can use the PEM fuel cell heat for the reformer to power the needed heat for the reformer. In the next generation, we wouldn't need to burn a part of the fuel. We can have fast startup time because it's just short heat-up, quick heat-up. And we produce between 0.8 and 0.9 kilowatt-hour of electricity per liter of formic acid. And with this low temperature, we can reach, with plastic vessels, low weight. On cost, we have simple CO cleaning stage. As I mentioned, if we go towards plastic, we can use plastic reactor, which is easy to manufacture and handle, and the control of the reaction is really simple. So we can state that we have ease of use because of the formic acid, safer and less toxic than methanol, and easy to transport in PE tanks. So we have made this demonstration unit. Our intent is to develop a 10 kilowatt reformer unit as a product development and go into field test for later complete system prototyping. Another point that Professor Lorenzi mentioned earlier is the hydrogen filling station, because the reaction can be made at high pressure and produce directly compressed hydrogen, for example, for filling station, and allow easy transport from plants to filling station. Because, yeah, we can reduce the compression losses, we can recover the CO2 and be CO2 neutral, and we can have 1 ton of hydrogen per truck, the equivalent of 1 ton per hydrogen per truck for transport. Okay, so this project is, this demonstration is one block within a full cycle and storage. I need to be quick. I'm almost finished. So, with the actual demonstration, we had not recovered the CO2, but this is possible with highly concentrated stream of CO2 or capturing CO2 from industry. We could produce renewable formic acid and then go into close the cycle and have energy storage to convert renewable electricity into hydrogen stored in the form of formic acid. Let's finish. Oh. Okay, a quick, just 2 slides. Sorry. So my last slides, our next project. Sorry. The idea would be to develop the rest of the cycle, to store electricity, for example, during summer into formic acid or formate salts, and during the winter use the stored hydrogen into this form, into heat and electricity for the winter. So this is it for my presentation. This is our project of the last years and the future that we want to implement. And for this, I just want to thank the Swiss Federal Office of Energy for the financing support, the team of Professor Lorenzi for the very efficient collaboration and transfer of this catalyst into product, and our team for the efficient work. Thank you very much.